To our mole conversion unit review. So in this video we're going to go over question 13 here, and then we're going to run through using our grape strategy to kind of pick apart more complex problems. These are some of these challenge problems here at the end. Alright, so let's start with question 13. So question 13 describes the sodium concentration in seawater is 0.469 m, capital M. The way we say it is 0.469 molar. Alright, so first I'm going to list that as a given quantity. So we talked in class about how we write concentration of quantity with little square brackets, and so that means concentration of sodium ions. Of sodium ions. The ion, of course, means it's a charged particle, meaning it's a positive or a negative quantity. Okay, so the concentration is equal to 0.469, and I really encourage you, if you ever encounter a capital M value here, you take a second to rewrite it in moles per liter, because there's a lot of kind of new terminology when we deal with these ideas in chemistry, and it can be easy, if we're thinking about lots of things at once, to think this represents a number of moles, but it actually represents the number of moles in 1 liter of solution. Okay, so question A. Oh, you know what? I'm actually going to draw a picture of that. So before we move on, so here's like a 1 liter beaker, right? And so there's 1 liter of seawater, and the amount of, there's lots of other ions floating around the seawater as well, lots of minerals is what we typically call them. There's lots of sodium ions kind of floating around, and if we took all those sodium ions, there's about 0.469 moles, or less than half a handful. So there's a less than symbol. Half a handful of sodium. So you can picture a handful of salt, or you can think of table salt, really. And but really only think about the sodium parts of table salt. And about half of a handful you pour it into a whole liter, like maybe a Nalgene water bottle, and that would give you seawater. So I think it's important when we see molarity values to take a second just to sort of visualize what that means. Okay. So question A here asks us what volume of seawater will contain 12.31 grams of sodium ions. Okay. So it looks like for question A, we're also given that we have 12.31 grams of sodium ions, which sounds, I don't know, something like half a mole. Anyway, because I'm picturing about 12 grams, I'm like, well, that's probably about half a handful. That sounds okay, it sounds about right. And the question is, what volume of seawater will we use? Okay. And so required the volume of seawater. Okay. So fine. Let's move to our heart of the mole sheet at this stage and just see if we can orient ourselves, figure out where we're starting and where we want to get to. So if we're given 2 values, right? We're given the concentration and molarity of seawater. And if we look on here, we say, well, where is molarity found? Well, molarity can be used as a conversion factor. It allows us to convert between moles of a quantity and volume, or volume of your solution, to the number of moles of your solute, right? Okay, so that's this part. So we're given this guy here. Great. we're also given a mass, number of grams of sodium. So that means we live here to begin with. And then we're asked to find the volume of seawater. So there's our word volume, which shows up 1, 2, 3 different places on our conversion sheet here. And we just need to make sure we can understand which position, which volume is relevant to us here. We're talking about the volume of a solid. Well, seawater isn't a solid. And it's not a pure liquid either. It has water in it, but it also has other things floating in it, right? And that means it's not pure liquid. Pure distilled water might be considered a pure liquid. We're not talking about the volume of a gas, which means we're talking about the volume of a solution. And that's what that concentration means, right? It means we have some solute dissolved in our solution. Okay, so that means we're starting here, and we're going to try to get to here. It looks like to do that, we're going to need the molar mass of our solute, and we'll need the molarity, which is given. Okay. So I'm going to start with 12.31 grams of sodium ions. And then I'm going to need my molar mass, right? So if I look at my periodic table, the molar mass of sodium is 23.0 grams for every 1 mole. And a sodium ion, it has 1 less electron. But electrons are so much smaller than an atomic mass unit, an AMU, such that we find that totally negligible. It's not in our, we only have 3 sig figs here. If we reported more sig figs, actually maybe in the hundredths or maybe thousandths of a gram, we might notice a slight difference because we have 1 less electron. So that's for every 1 mole of sodium ions, and our mass cancels out. Great. So now we've got units of moles, and we want to find the volume of the solution, so we're going to use our concentration here. And we typically want our moles. This is 0.49 moles for every 1 liter. And so we want our moles to cancel out, so we're going to say our moles of sodium ions are going to be down here. And we know this, and we want volume in liters of solution up top here. And so we say, okay, this is 0.469 moles of sodium for every 1 liter of solution, like so. These guys cancel out. And then we should be able to find what volume of seawater, which is our solution, will help us. So let's get our calculator out, type in 12.31, and we'll divide by 23. And we'll divide by 0.469. And, oh, interesting, we get about a liter. Looks like we got 4 sig figs, 3 sig figs, 3 sig, should round this to 3 sig figs. So it says 1.14 liters of seawater. Contains 12.31 grams of sodium ions. Okay. So let's take a look at question B now. So question B asks, how many sodium ions are there in a 0.073 mil sample of seawater? Okay. So where are we here? What we're given is a volume of our seawater. So we're given this value here. And where do we want to get to? Well, we're asked how many sodium ions. How many? Not how heavy, not how much space, how many. And that's a number of particles. So we want to go down to the heart of the mole and then up to the number of particles. In this case, ions. Okay. So we're going to begin here. Now, we want to watch out. Volume of a solution calls for liters, and we have milliliters here. So first thing we're going to need to do is turn that into a number of liters. So we're going to start by saying 0.073 mils of our solution, right? And we're going to first convert that into liters. I know 1,000 mils are in a liter, so it's 1,000 mils for every 1 liter. And then we're going to use our molarity to cancel out units of liters and replace it with moles. The molarity of our solution is 0.469 moles for every 1 liter. Four, 6, 9 moles sodium for every 1 liter of solution. Okay, so mils cancel out, liters cancel out. We've got moles now, and we want to find how many sodium ions. So we're going to say, well, there's 6.02 times 10 to the 23 sodium ions in a mole of sodium ions. That's our last step. So 6.02 times 10 to the 23 sodium ions in 1 mole of sodium ions. Okay, our moles of sodium ions cancel out, and we'll get some value, some number at the end of the day. We'll just punch that into our calculator here. So we're going to start by 0.073 mils divided by 1,000 equals, and we're going to multiply by these two quantities, times 0.469 times 6.02 times 10 to the 23. And we should get 2 sig figs worth of values here from these 2 sig figs here. And so we're going to get 2.1 times 10 to the 19 sodium ions and 0.073 mils of seawater. All right, there we go. Okay, now we're going to move on to our challenge problems. Now to do this, I'm going to try to just very patiently go through each of our steps in grapes. And I'm going to use a highlighter to do that. So let's start with our challenge problems. Okay, so question 1. We'll start by reading it carefully, maybe even rereading it. All right, so we've got the Saturn V rocket, which is the most common rocket that is used to launch things into space, by NASA at least. They use liquid oxygen and liquid hydrogen for fuel in the 2nd and 3rd stages. Okay, great. Saturn V rocket used 1.2 million liters of liquid oxygen fuel. And the question is, what volume do the oxygen molecules occupy? What volume do the oxygen molecules occupy if they were allowed to become oxygen gas at standard temperature and pressure? And we're also given the density of liquid oxygen. Okay. Okay, so let's start by our grapes step. So G, we're given a few values. We know we have 1.2 million liters of oxygen, and that's a liquid, so I'm going to put a little L there for liquid. We're also given the density, and that's a volume. And we're given 1 liquid O2. It has a density of 1.141 grams for every 1 mil. Okay, great. And that's all we know right now. We could probably find some other things out. Let's ask, what are we required to find? And we're required to find the volume of oxygen molecules if they became oxygen gas. Oxygen gas at standard temperature and pressure. Okay, So the volume of O2 gas at STP. Great. Now, I'm going to take a second because with challenging problems, maybe this isn't so challenging for you. I actually think in some ways this isn't as challenging as some of the other questions. But let's treat it as if it is challenging. So the first thing we should do is draw a picture, right? So I can picture a giant beaker. So it's very big. There's a human. And it has some amount of liquid oxygen, right? 1.2 million, or times 10 to the 6 liters of liquid O2, right? And the question is it just O2s kind of floating around? And O2s, just whatever. Great. And we're going to allow that to, so liquid oxygen is kept very cold in order to make it a liquid. So if you heat it up, it'll eventually turn into a gas, right? And this is all these O2s in a gas. This is oxygen gas at STP, right? So 0 degrees Celsius. And you can breathe at 0 degrees Celsius, right? That means oxygen is a gas at 0 degrees Celsius. Okay, so there's our picture of what's happening, and the question is, what volume is this cloud, right? That's what we're really asked here. What is the volume of this cloud? Okay, so let's just figure out, you probably pieced together where we want to get to on the sheet. We're talking about the volume of a gas at standard temperature and pressure, so we're going to try to get over here. This is going to be the volume of oxygen gas in a cloud. The question is, where are we beginning? So we're told a volume, but it isn't the volume of a gas. And the question is it a solution, or is it a solid or pure liquid? If we look, we say, okay, well, this is not a mixture. It's not like our seawater example here. This is literally just pure liquid oxygen. It's a pure liquid. So we're going to start here, and we're going to find the mass to the number of moles, and eventually the volume of a gas. Okay. So in that way, I'd say this question is a little bit less challenging than maybe some of the further ones, because it's pretty linear in a lot of ways. We're just going to kind of trace our way along. It just happens to be there's 3 steps in this conversion. Okay, so I'm going to start with my 1.2 million, or times 10 to the 6 liters of oxygen, and it's a liquid, right? And I'm going to find first the mass of my liquid oxygen. So to do that, I multiply by the density. Oh, I see, that's one of the reasons this is challenging. Our density is expressed, sorry, I wrote this question last spring. The density is given in grams per milliliter, but our volume is actually in liters. So first thing we're going to have to do is either convert our density or convert our volume into milliliters, or convert our density into liters. I think it's going to be easier to convert our volume into mils. So that's the first thing I'm going to do. I'm going to say, okay, for cancel out liters, I'm going to replace it with milliliters, and I know there's 1 liter for every 1,000 milliliters. So that's the first thing we're going to do. Now we've got milliliters. So now we can use our density here. And if I multiply it directly, it says 1.141 grams O2 for every 1 milliliter of oxygen, right? Okay, great. And that gets us to a mass, like how heavy that 1.2 million liters of oxygen would be, right? It tells us how heavy it would be. Now, I want to find out how many moles that is, because eventually I want to find out the volume if it's allowed to become a gas cloud. So I need the molar mass of oxygen, O2. So maybe we'll find the molar mass of oxygen. So it's going to be 2 times 16.0 grams per mole, because there are 2 oxygens in every O2. So it gives us 32.0 grams per mole, which we're going to use here. So I want to cancel out my grams, so I'm going to put those on the bottom. 32.0 grams of O2 for every 1 mole of oxygen. And then lastly, from moles, I want to find how many, the volume of this gas. So I'm just going to say, well, each mole at standard temperature and pressure occupies 22.4 liters of space. So it'll be 22.4 liters of O2 gas for every 1 mole of O2. And lastly, I just checked to make sure my moles cancel out. And I've got volume of our oxygen here. So I'm just going to put this into our calculator at this stage. 1.2 times 10 to the 6 times 1,000 times 1.141. I'll multiply by the tops, 22.4, and then I'll divide by the bottom, 32. And we get some tremendous volume. So how many sig figs should I have here? 2, infinity, 4, 3, 3. So it looks like 2 is the smallest number of sig figs. So I could write this as 960 million liters of O2 gas, or I could rewrite it as 9.6 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 liters of O2 gas. Oops, I was a little off screen there, I didn't realize. Okay. So move on to second challenge problem here. Okay. So what do we have here? The volume of a uranium dioxide fuel rod that gets used for nuclear reactors. Okay, so the volume of a uranium dioxide fuel rod is 3.926 liters. And here we see a picture of some fuel rods, and they're all bundled together. Each one of them occupies 3.92 liters of space, so these are actually quite big. All right, we're told the density of uranium dioxide, and the question here is how many oxygen atoms are in a 37 rod bundle? And we can see they're bundled here in this picture. All right, so I'm going to start by listing my givens. So I'm given that we have, first of all, that we have uranium dioxide. So maybe first we should write that formula out. 1 uranium, 2 oxygens. Okay, so we're given the density of uranium dioxide, which is 10.97 grams for every cubic centimeter, right? Or for every milliliter, in other words. We're told there are 37 rods per bundle. Okay, and we're asked about, we're required to find the number of oxygen atoms. Okay. So, we're given also that the volume, 1 fuel rod is equivalent to 3.926 liters of space. All right, that's how much space it takes up. Okay. So, all right, there's lots happening here. So where do we start, right? Okay. So there's a few different ways we could probably go about beginning. I'm going to draw a little picture here before I get started, though. Try and visualize the situation. All right, so we know we have one fuel rod, right? And that occupies 3.926 liters of space. And you can picture that being maybe 4 nalgons worth of space, approximately 4 1-liter water bottles. Okay. And it's made of uranium dioxide, right? So that means for every one uranium dioxide, there are 2 oxygen molecules. Now, we know this is in a bundle of rods, right? So this is my wonderful drawing of a bundle. And that is, there are 37 rods in one bundle, right? So, okay, great. And the question is, how many individual oxygen atoms are there in all this stuff, right? So what I want to do is I want to be able to sort of take a magnifying glass, right? And look at that and say, okay, if this is a uranium oxide here, and there's a uranium dioxide here, and uranium dioxide here, you know, how many oxygens? Okay. So let's take a look here. So maybe with all this information, there's one thing we know for sure. We're asked how many oxygens. So we're probably going to need to find out how many uranium dioxides there are. Okay. And looking here at this information we're given, looks like we're given a bunch of information, but we know the volume of one fuel rod. And so maybe we can start here, and it looks like that's going to be a solid, right? We can imagine a rod is a word we use to describe solid things. So we're told the volume of a solid here. So eventually we need to trace our way along this path. Now there will be a few hiccups along our way, but that's kind of where we're going to start. Now, that will be fine, but we need to remember that there's actually, we're not looking at one rod, we're looking at 37, right? So I might start with one bundle. Go. So one bundle, and I know there's 37 rods for one bundle. So you could start with 37 rods if you want. Oops. All right. Now, we know the volume of that rod, so maybe we can start by turning that into a volume, and then we can get ourselves onto this sheet. Okay. So we're going to use the volume here, which is 3.926 liters for every one fuel rod. I'll just say rod. Looks like we're using the word rod. Okay. And we're told a density of uranium dioxide is 10.97 grams for every cubic centimeter. So I need to turn my number of liters into a number of cubic centimeters. So first thing I'm going to do is turn to milliliters, because I know 1,000 milliliters is equal to 1 liter. And also I know that 1 cubic centimeter is equal to 1 milliliter. Take a second to just cancel out units, bundles, rods, liters, milliliters. Now I've got cubic centimeters. So now I can use my density quantity. And I'm going to multiply by that density to get to the mass. So I'll multiply. The density was 10.97 grams of uranium dioxide for every 1 cubic centimeter. Okay. Great. So we're getting there. Now this question is starting to become a little bit more normal. We need to find the molar mass to convert that into a number of moles. Then we'll find the number of uranium dioxides, and from there we'll find out how many oxygen atoms there are. Okay, So this is getting a little long, so I'm actually going to continue this conversion problem over here. So the next conversion I'm going to need to do is cancel my units of grams to replace it with moles. So to do that, I'm going to find the molar mass. So 1 mole of uranium dioxide is going to occupy, so I need to find the molar mass. So molar mass of uranium dioxide. The uranium molar mass is 238 grams, 0.0, looks like, grams per mole. And then we're going to add to that 2 oxygens, so 2 16s is 32.0 grams per mole. And we do that, we get 270.0 grams per mole. So 270.0 grams of uranium dioxide for every 1 mole of uranium dioxide. And then we can find the number of actual uranium dioxide particles. So to do that, we're going to do 6.02 times 10 to the 23 uranium dioxide molecules for every 1 mole of uranium dioxide. And the last thing we need to do is be able to convert between our number of molecules of uranium dioxide to the number of oxygen atoms, which is to say there are 2 atoms of oxygen for every 1 uranium dioxide molecule. Okay, so just check to make sure my units cancel out here. My grams of uranium dioxide cancel out, moles of uranium dioxide cancel out, molecules of uranium dioxide cancel out. And so we'll just start punching stuff in. 1 times 37 times 3.926 times 10.97 divided by 270 times Avogadro's number times 2. And so we should expect, well, how many sig figs should we have here? Well, looks like I've got a few quantities with 4 sig figs, some infinity sig figs, 4, 3, infinity, but here we have 37, which is a counted quantity. Now, specifically, we would say there's actually going to be exactly 37 in a rod, but without that piece of information, I'd say we should act as if there's 2 sig figs here. So 7.1 times 10 to the 24 oxygen atoms. Okay. So we'll continue the next few in the next video. Good luck studying.